for this presentation from our guest speaker, Sam. He's going to be talking about his work at Intel, AI, and then following this, we're going to have a reading discussion on the AlexNet paper. You guys should have seen that paper in the Slack. If you haven't seen it, you can go in the Slack, download it really quick, and then we can talk about it. So let's give a round of applause to Sam.
All right, everybody. So, pretty much what I want to do is kind of have a little conversational presentation on what I do at Intel and mostly how I do that. As I can probably tell, I'm not too far removed from where you guys are at now. So, and I'm not studying the degree with Windows machine learning. Probably very little in this room, but I kind of want to tailor this to people who are looking at machine learning as a possible future job and what that looks like, either after graduation and how to get there. So hopefully you guys can get some value in that, and I kind of welcome everyone to learn about questions that you guys have talking about these things, just so you guys everything's clear and things like that. All right, so my job at Intel is kind of unique in the sense where me and the team I'm on and what I'm doing is I'm not supposed to do, or what I do is look at the current research that's going on. I make connections with researchers that are working on things that I think have potential, and I take what they've done, work with them to integrate and see how that would work on our processors in the future. So I don't know how much you guys know about the chip industry, but it takes around 2 years to 3 years to build a chip. So in a fast-moving industry in AI right now, you don't know what's going to look like in 3 years. You don't know what's going to be valuable in 3 years. You really have to be on. And Intel, they have groups that implement a lot of things, but they don't necessarily have a group that these executives and chip makers can go to and ask, what do we need to start working on now that will be beneficial in the future? And Intel made some mistakes along the way that the chips they created now that I'm working on now, or trying to get to customers now, don't necessarily have everything embedded in the hardware to make some of these neural network operations fast. So what I do and kind of what I'm building a team right now to do is really make connections with researchers, see what's going on, and then kind of integrate that. So I have a good kind of scope of the general position that AI is in now, and kind of the general knowledge about where it's going.
So Intel making chips for AI, that means trying to compete with NVIDIA, for example.
Yeah, so that's a good question. So NVIDIA was positioned super well because it can do really major multiplication super well on graphics. That's how the graphic processing is. So they kind of stumbled upon the whole line of kind of AI coming up in algorithms being developed. So Intel right now doesn't make anything to train any that we think they did that well. We are creating a neural network chip specifically for that Nirvana, but that hasn't out yet. They're rolling on soon, and generation 1 and things take time. What Intel focuses on now is we own kind of a whole suite of chips from the server level processors to things like this, which are NVIDIA's chips, which are this thing's tiny, probably like size like a fingernail, and run one top on it, extremely low power. So if you have these in a position from your robotics at the edge, things that are taking in the engine, run neural networks right on the actual device, and then it gets emitted from that and pass it back to servers. So that's kind of the strategy we have now with inference. So you train on GPUs, and then you pass it to some of our compilers, and then we run it on any of the our target users only for inference. So you don't necessarily train for chips. So a little bit about how I started with Intel. I started working on this specific chip when I was in high school, just doing just running different vision algorithms for a research and development group in Santa Barbara. It was like an internship for the after school and over the summers. And that's kind of how I got my connection to Intel. So when I came up here, they had bought this company called Movidius. So I had to connect through that, and I asked them if they were going to hire me, and they did. So I didn't have any AI knowledge or machine learning knowledge whatsoever. I was just in there, kind of doing whatever the hell they wanted me to do. Like I was just random Python physics, random stuff like that. I mean, just put something my ass off. And but with time, that's how I got into it. Was just by I kind of started building up around machine learning, and I started like reading books, and I like the visual deep learning book. Most of the stuff coming way over my head. But like with time, around 6 months, I took a class with Andrew. We were able to create an independent study course with a math professor. They were able to teach us kind of how to learn this stuff, and it just took some time. And after a little bit, I knew kind of the basics of it, and then from there, I was really able to just do random projects, build on top of it, and then I was asking myself, hey, like, I kind of know my stuff now, because I started getting projects in this area, and they slowly started leading me like AI projects, and from there I built my expertise and have gone with it, and now I'm in a full-time position only doing AI stuff. So what does what the hell do I even do? So my first question here, and I'm going to go through some of the different projects where I'm currently doing at Intel, and it'll kind of shine some light on, I think, the wide array of things that machine learning can do, and the wide array of things that's going to be implemented. So I know passions and all these different things, and maybe computer science or whatever isn't your number one passion. You kind of want to work on other things as well. Well, with machine learning, like, it's really going to enter the workforce, or it's going to enter everyday products in all these fields, in all sorts of different things. So if you're like really passionate about, for example, like philanthropy, there's going to be plenty of opportunity there. Like art, robotics, medicine, and even gaming. These are just the projects that I've personally worked on. So it's going to be way wider than that. So first and foremost, I'll talk about gaming. And one thing that I did at Intel is we have our chips in almost all these gaming computers, right? So one application or one thing that's coming about now is called deep reinforcement learning. And this is where you have an agent and it interacts with an environment, and then it'll just learn from interaction and from experience, kind of like how we learn. And you can build these agents and kind of put them in any environment. And right now, gaming is the center for this because it's easy to create almost real-life environments with gaming. You don't have to actually have a robot going around in the actual world and screwing up everywhere and trying to learn from that. So one thing I did was I created Google actually released a football environment, like a soccer FIFA environment, and you can have these deep reinforcement learning agents play, and then you kind of develop your own algorithm and release them to this environment. So one thing we did was we built these reinforcement learning agents to play against you in FIFA, and it'll learn kind of as it goes. It'll get better as you play it, and it can play against itself to kind of just exponentially get better. And so we built that. We worked with Unity to build an environment for that, and now they opened up that machine learning or the reinforcement learning environment. Now anyone can go in. There's a bunch of games you can design, and you can create your own agents through that. And this stuff is all open source, so even you guys can go and play around with this stuff now. So that's one application I did. Another one was just with this style transfer, this Mona Lisa looking painting. I didn't actually do this. I just pulled it off the internet. But what I did was we needed to. This was, I think I did a year and a half ago, and we have these things called the neural compute sticks, which are these little USB devices, and you can just kind of plug them in, and they have one of those Movidius chips that shows inside them. And you can run neural networks on like a USB. You don't need to connect to the cloud, or you connect to some cloud TPU to bring the computer and have to pay for that. You can just run it on like $100 USB. And we want to kind of show the applications for this and fun projects you can do with it. So one of them was this style transfer. So what the network does is it learns a particular artist's style and how they paint, which is in this case this middle one. So just trained and looked at that and learned that style. And then what you can do is feed it content, and it will apply that painter's style to the content you feed it. So in this case, the content is the Mona Lisa and the style is the other thing. I combine the two at the end. And this is kind of how all the Snapchat filters work, how it's similar to, I mean, you can do all sorts of applications with it. There's actually even art paintings now that do this and are physically sold, like the physical robot that paints it, and then it's sold for like millions of dollars. So yeah, so I mean, if you love art, you can get into that. That's another project. Something I'm doing right now is working with GE Health, and what they do is build these big MRI machines, and one thing kind of nurses and doctors have to do that's tedious, make sure that everyone is in the machine and in a correct position, and they have to kind of monitor that all the time and like be with the patient and kind of look at him inside with cameras and make sure he's positioned well. And one thing that AI can help with in that case is just get his body pose from these neural networks, and it'll immediately be able to detect what part of the body is not positioned right and correct that. So it's a small application, but that I've done. But in general, machine learning and artificial is being used all over the medical field for optimization of processes like that, to give doctors the ability to actually just do their job in a tedious task, and also to help them like detect tumors and anomalies like that, help them in the diagnosis. Yeah.
Okay. Intel, as a computer chip company, how come they have you doing all these different types of AI projects? Like, they seem kind of unrelated to each other, except that they all do AI. So how come you're pursuing all these different types of projects?
Yeah, so one cool thing is with Intel is that they just make chips, but they need to market their chips to specific applications. So and those applications, people who like want to know the capabilities and everything, like GE Health per se, there's not a lot of machine learning engineers out there. It's a new field, it's a difficult field to get into. So they consult us a lot on like, oh, can you guys even do this? Can your chip do this? They ask us these things, or we have to go out and be like, oh, our chip can do this, but to actually prove it, we have to build demo applications and build these things and test them, and then we show that, oh, like, look, our chip can do this at this speed or this power consumption, and then they're like, oh, cool. They take what we have and then build on top of it. So even though we're not specifically like doing just software applications, we're trying to sell these chips. We have to build software applications so our customers, the people who buy the chip, know what it's capable of doing. Yeah. So another project I did was the still robot. We just integrated a little system that pretty much you look at the robot, it looks at you, and then whatever you do, it'll imitate you in real time. So this is another case, just a demo application to show that we can run these different algorithms in real time in like a robotic setting on this little robot. The robot doesn't need to be connected to the internet, the cloud, or any of these things.
And all the projects you mentioned using multi-use chips?
Yeah, so not the FIFA game and GE Health, not that one, but the rest of them. Yeah. So okay. Yeah.
So for someone that wants to kind of do these, so I mean, it's no secret that increasing hardware is becoming a bottleneck of learning application. And as students, that it's expensive for us to deploy anything. So the obvious, or I don't know if it's that obvious, but for me, it leads me to believe, okay, maybe I should build my own chip. Is that like feasible? Well, and is that number two? Is that although it won't be as good as an industry standard, like what would be, how would you go about that?
So I think building your own chip would be really hard. I don't know. I'm not a necessarily a hardware guy, but I know the teams that do build this, and they're massive teams, and it takes years of planning and years of debugging and to get it to the state it is in now. And to even do that is extremely difficult. So I don't know how makeshift chips would work, or how well they would work, or if it's worth your time. But I know for machine learning, especially, you do run into this bottleneck a lot, and you have to kind of know what chips are out there and what application you want to do, and then buy them specifically for that application. And like let's say if you want to run a network that is massive and huge, like just like you need like a lot of memory to even store it, then you wouldn't go with like a Movidius chip or anything like that. You'd have to go probably with like a GPU, or I know High Silicon makes really good higher end chips. Even Intel makes some better higher end chips as well. So there's a lot of stuff on the market, and I think kind of looking around for it is important. And the fact that these things take 3 or 4 years to build, that also creates a lag in the availability of things. But artificial intelligence, deep learning have come up in the past 10 years and extremely fast. So I think these chip making companies will get it and start releasing things that are better. Break your wallet quickly.
And you also said that the Movidius chip was particularly useful for inference. So as far as I know, inference capabilities are useful for like lessening the amount of data you use to kind of get to your conclusion or the prediction or whatever the goal is. So how is that useful? How is inference useful in your projects versus a regular GPU?
So for inference, it's only matrix multiplication. You just have an input, goes through all the matrix multiplications, that's fully trained, and your output comes out. For training, you have to calculate the gradient for all those, and then apply the gradient to everything, and that calculus involved takes way more processing power. So for our chips, or especially Movidius chip, let's say in the case of, I'll just do the case I talked about, which is the one on the far left or right for you guys. This was called TrailGuard, and we worked with a nonprofit organization to prevent poaching. So poaching is when these people come out and kill endangered animals and sell like their body parts. And one thing this company or this nonprofit organization is doing is installing these camera traps throughout these poacher trails. And what they would do, if there's any motion, would take a picture and send it back to the rangers that are nearby. One, that's a lot of data to send back. The picture it takes a lot of data in it. And two, a lot of things in the forest creates motion. So send a bunch of garbage back to the rangers, and then have to go through thousands of images to actually find, oh crap, there's actually a poacher here. And by that time, it was already too late. So they would catch these guys usually on the way out, or after they've already killed an animal. So it's kind of unnecessarily working very well. So we worked with them in this case to so what it does is, now that if there's motion, it takes a picture, and you're able to run we developed a poacher detection algorithm, kind of person detection, kind of fine-tuned. And so when there's actually a poacher, then only then do you send that data back. And only then do the rangers, the more they get an alert that there is a poacher here, go act now. So that is kind of what this lessening of data is. And for other cases, you wouldn't send back a full image, you would just send back some metadata or a feature set of what it sees. So rather than sending the whole picture, you would send just like a convolutional filter for the output there, and then maybe another neural network will handle the bigger computations after it's gone over the network. But right now, the network is the big bottleneck. So reducing the amount of data you send back is kind of important. Yeah, okay, so those are kind of the projects I've worked at Intel. I've worked at Intel, but I mean, they do a lot of stuff with research divisions there. I don't necessarily do research right now. I might move into it a little bit, but I mean, there's a lot of different things you can do. You can, I mean, understanding this stuff, I think, is going to be very important because everything is going to run some sort of neural network. So don't necessarily need to know how to change it and what those changes are going to do, but knowing what's going on so you can kind of debug the situation and know, like, well, what could this problem be? And being familiar with the space is going to become increasingly important in the future. So, good that you guys are curious about it. Yeah, that's kind of what I was talking about before. Kind of we're just at the tip of the iceberg. A lot of people thinking, oh, maybe AI and machine learning is just hype. Like, oh, it's a bunch of hype. Like, kind of like, can't even use the internet as an example. That's huge too. But yeah, so right now it's very much like the tip of the iceberg. So we've done really well on for image recognition, person detection, and things like that. But new research is coming out every day, and only research is what's coming out of it right now. So I mean, you read about white papers, you read about kind of these researchers getting 1% more than this other researcher. That's not too inspiring, and that could kind of demotivate people from going into the space. But I think nobody has really done too many applications with the data that is coming out of these networks. I mean, being able to put these networks together and create a system behind it using what's going on. I mean, our computers now, for the first time ever, can understand the world and has a way to understand the world, kind of like how we do. Before, it was only reacting to sensors, but now it can react to its experiences, it can react to what it sees. I mean, this adds kind of ripping apart the whole layer of capability. So in using that data that's coming out of these neural networks and understanding what's going on, build a lot of applications stuff on top of it. So you don't necessarily have to be in the research position to like doing stuff. Yeah.
Just curious, what does your day look like at Intel? So like how much of it is reading, how much of it is like coding, what do you do while you're waiting for the model train?
Yeah, so I could like walk through what I did today. So I mean, I go in the office in the morning, I usually start by going through Reddit. So Reddit has a lot of researchers on it. I mean, it seems like kind of weird to be on Reddit while you work, but I mean, I need to know what people are talking about when new research has come out. And people are talk a lot about that stuff every day, every week. You can really get that update.
Which are these?
The subreddit, I think the machine learning, that's the best one by far. I go on that specifically. There's reinforcement learning as well, natural language processing. But yeah, there's a lot of good subreddits. So yeah, so I go on Reddit, kind of, like not too long, depends on if there's good updates or not. That kind of gives me a good pulse of what's going on and what people are interested in. And then after that, I usually have a meeting with my team, like once a day. We just talk about kind of what we're working on and different things that are going on. If there's a paper or something that I think was promising, I'll read that paper, and if I think it's good, I'll create a report on it and put it on our team's internal website and contact those researchers to get more information if they want to have a meeting or something like that. And if I kind of get past that stage or see things that I think are going to be promising for whatever chipset or anything like that, I'll code up a demo or there's usually like GitHubs and things attached to these papers. So I'll go in, kind of get that working and see how I can optimize that for our chip, get it working on our chip, and maybe create a demo out of it, or create a training environment so we can build on top of their research and show its capabilities for our application. And this is a network that's like brand new, and we don't really know how it works, but we know it's promising. Like right now, algorithm came out called BERT, and the natural language processing algorithm. And that couple key things in there that makes it really revolutionary. So even though this specific BERT algorithm might not be the one that we want to use, but this algorithm is going to be what future algorithms are going to be based on. So knowing what's going on under the hood and trying to apply that and kind of getting on this building kind of repertoire around that is important to see how we can optimize it. Like a research paper came out at Intel last week about it's a really big network, so how do we reduce the size of that? So we did this thing called quantization, in which makes all these floating point 13 operations integer 8 through a training process, and that reduces the size by 4x, a lot. So now we can fit these kind of on the edge, and yeah, so different things like that. So I do a lot of coding, do a lot of reading, and a lot of meetings.
Speaking of demos, can you see the demo?
Yeah, so I have a demo. Yeah. Andrew told me I need to bring a demo in case I'm a big snore up here. So this is just like this is going to be running. There's a couple different algorithms we can run, but I think the coolest one is this thing that will take your head pose, kind of what way you're facing. It's able to detect how old you are, whether you're male or female, and your emotion. So if you're happy, sad, surprised, like that. And then all this, like this thing doesn't have any big compute on it. I mean, you can't run, any neural networks directly on this mobile thing, but if you have this attached, you'll run it completely on this chip. And then just feed that data back to the computer to do whatever logic you want to do.
Are you able to plug it into the
No. Doesn't have HDMI. I don't think so. I don't think it has HDMI.
Usually never happens. Do you happen to have Zoom on your laptop?
This you can do too. I doubt it. This is like a demo computer, so
okay.
Yeah, I don't. I'll just like pass it around after I start it.
It goes to show that normally this mini notebook would not be able to run any AI application.
Yeah, exactly. If you want to run it on the cloud, you would have to always have good internet connection, and that's
How's it?
Huh?
I just checked the reach.
You pass that around.
It's like $68 on Amazon.
Jesse, can you hold it? Show you.
I mean,
You can pass it to me.
yeah.
Yeah, so I built that demo as an intern a year and a half ago or something. So
Yeah. Well, I came here a little bit late, but so if my question was already asked, I'm sorry, but
Yeah, I don't want
they
to.
directly
did I directly get it?
Yeah.
No, so I started there as an intern while I was at school here, and
were you undergrad?
yeah.
What's your name?
Computer science. Yeah. So so I started as an intern, and I wasn't studying machine learning. I was just doing random stuff with them, and anything they could give me, I tried to crush out as much as possible, and just on my own try to read kind of what you guys are doing today, pick up AlexNet, read AlexNet. If I didn't understand anything going on in there, you kind of get into that thing, and you just keep going down that rabbit hole as long as possible until you get to okay, everything's just basic math. And then, and then once you understand all that, then it's easy to kind of intake all these new papers and see what's crap and not crap quick. And then from there, you build a foundation kind of what you want. So I just did that, and then with time, I asked my manager, hey, can I get some machine learning projects? Can I get into the stage? And then he gave me more machine learning projects, and when I did well on that, kind of built in the 9 months.
Was it like
Hackathon? No, nothing like that. Yeah.
is it like a school project?
With Intel?
Yeah.
No, they're as an intern there. So yeah, so I would just tell them I just told them I want to be in that space. My manager has been able enough to try and make that happen. Smaller projects at first, test my ability, then from there I
So you just have a bachelor's degree, is that correct?
Yeah.
So what do you recommend to people that are trying to get into like machine learning as a field? Because usually one of the prerequisites for math is minimum of master's, PhD.
Yeah, so that's what I kind of wanted to shine some light on today, is that you don't necessarily, I think that's a false statement where you need a PhD or a master's to get into machine learning. I think if you want to get into a research position and really be on top of the kind of creating new algorithms and then posting white papers about it for that company, then if you're trying to move into that position, then sure, I think that's valuable. But honestly, like I think machine learning engineers are hard to find. One part because of that fallacy, and two, because of kind of the math behind it is kind of scary. But honestly, if you just read these textbooks and understand what's going on, be able to talk machine learning, like read a white paper, if you're able to read an entire white paper and know kind of the essence of the network and essence what they're trying to get at, you can get any of these jobs, really. I think you have to go to the PhD and everything. Those programs, one, the professors are being sucked out to these bigger corporations, so they're losing value because you're not studying under like the best of the best for these PhD programs. And two, companies kind of just need engineers that know machine learning. So as long as you know it, they won't care for it.
So how did you and Andrew end up organizing your independent study classes?
Yeah, so
is there research involved there, or?
Yeah, so there's actually no research. So with CS, you can do like an independent study class, as long as you have a professor and you can create your own curriculum, and the professor agrees. And one of my math professors was really cool, really passionate about his students and things. So I just asked him. He went to his office hours and looked, like I explained that I'm super passionate about this. I really want to get into the field and everything like that. And then he said he'd be willing to do it only if I get someone else, because he didn't want to be babysitting me all the time, or working with me one-on-one all the time. Maybe it's a pain in the ass, but he said if I get someone else to collaborate with, then I can do it. So I knew Andrew through class, and he's a pretty cool guy. So
yeah. So I also came in a little bit late, so but what is your like position at Intel? Is it like a senior engineer? Because like the responsibility was pretty up there.
Yeah. Yeah. So yeah, I guess it's kind of odd, but yeah. So I'm not a senior engineer. I don't. I've worked a lot in industry. Like in high school, I've worked with them for a while now, and I've done projects that grew a lot in the company, like projects I kind of pushed for, and they elected said, yeah, you can work on it, and then they ended up being big. So I kind of proved myself at the company, and so now what I do is me and one other guy, we're building a team, and to be able to kind of be this thing I'm talking about, the pulse of AI research now, because of the process it takes to build these chips. You kind of need to have some foresight into where the industry is going, what algorithms are going to be important. So our job is to stay on top of that. So when any other team needs has some questions about that, or need some preliminary content on that, they come to us.
We're out of time. If you have more questions for Sam, if you can direct email to Sam. He's on our Slack, actually. So you can actually just publish him on Slack. So let's give another round of applause. Cool. So now we can get into our reading discussion on AlexNet.
Yeah. Everyone, Damien Gasson is going to share we take a discussion with our guys about AlexNet. So,
sort of the goal for the slide is to provide like a frame of reference for some stuff that's not really like gone over in depth too well. Sort of like a machine learning glossary for this paper in particular. Like it will help you understand some terms, but it's in no way like enough to help you understand like why the paper did what it did and why it was revolutionary for the time. So I still recommend reading this. It's just sort of like a tool that pushes you in the right direction.
We really want to emphasize that this is going to be a forum, an open discussion. This is not a lecture. We don't want to just be talking at the whole time because that would be pointless. So we want you guys to contribute, share your thoughts and ideas. So today is also a demo on how to read a reading discussion, because for future meetings, it's not going to be just us finding a paper and sharing it to you guys. We want you guys to take some initiative too, find some papers that really interest you, that you're really passionate about, and then you can bring those papers here and you can read a reading discussion as well. And you get practice discussing these really technical topics, explain to someone else. So please take this as a demo for the future.
So I'm going to switch to my slide.
We can do it.
Okay.
So let's just do this.
Okay.
So the introduction is just the introduction. Right, just summarize everything else.
So the data set that they used for AlexNet was really revolutionary. As you see on the slide, 15 million high-resolution images and over 20,000 categories. And this is really cool because previously, the state-of-the-art image classifiers used a lot smaller data sets. So having something that was actually better with a larger data set was sort of unheard of at the time. So that's one of the reasons why AlexNet is so revolutionary.
Have you ever heard of ImageNet before? Yeah.
So from what I understand, ImageNet had all these images that depended on random people to label them, right?
Yeah.
So I was thinking that, people aren't the most reliable. So there may be a case where like a significant portion of all these images are, let's say, poorly labeled or improperly classified. So I was wondering if that would have a significant effect on using this database to sort of train your model.
I do know that there are some very popular academic data sets that do have mistakes, and that's just a part of the art of machine learning. So because it's very hard to establish ground truth in this world, and so that's just how it works. So yes, and that's kind of what it is. Yeah, there's.
I have a question for everyone. What do you think might be one of the challenges of having a very, very large data set with many, many classes versus having a smaller data set?
Big question.
Say that.
Big question of the data.
What do you mean by that?
Like most of the cases, you change the images into a specific size, apply some transformations such as the 2D and transform. You need to do that on a very large scale compared to a smaller data set.
Something else that really killed it, especially for the time that AlexNet was done, is trying to fit as many images in a batch as possible. Otherwise, it's going to take forever, and you don't have forever. You have significantly less time than that to get it sort of optimized. So this is just an example of the categories that fit in each category. Pretty straightforward. So next part is the section that actually demonstrates how convolutional neural network can tackle down this AlexNet problem. CNN is basically the deep learning algorithm that takes the input image,
taking you through different layers and get the weight and the bias into the different objects and differentiate one image from the other. So for the convolutional layers, the first couple of layers is basically extracting the low level. Oh, I have one. Yeah, I have.
For those of you who did read the paper, you guys have any questions or insights, things you want to share about the paper?
Like whether the paper is difficult to read, something along those lines.
Impressions about the paper?
I mean, the general format of the paper was pretty straightforward. Obviously, I'm not going to lie to you and say I understood every detail because I didn't. But it's hard to have questions on something you don't really have great insight on. But I mean, general takeaways were that they use a lot of data and they had a lot of convolutional layers, and a lot of intensive computing to create a benchmark that had never been created before. And it is interesting because it makes it the paper almost implies that more layers and more data and more computing power is going to create better benchmarks. But I don't know if that's feasible, number one, or number two, that is the most accurate representation of the space.
Yeah, for those of you who didn't read the paper too, that doesn't mean that you can't contribute. You guys can still contribute, of course. It's like scroll through the paper, find something that looks interesting to you. If you guys just sit here, then it's not going to be as much benefit to you, right? But if you can contribute, then it's more benefit to everybody. Especially because
I read the paper, but I read an article about the paper. It was in so the best part, the new part about the paper is that they use the GPU. I think before that, no one had thought of using a GPU for training a network, and that's why the paper was being
That's a really, really good insight. The author of this paper was the first person to use a GPU for deep learning, and he actually went and coded up all the CUDA, and quite complicated. But yeah, this really ignited the revolution of using NVIDIA GPUs for deep learning. Great comment.
Does anyone know what was used before a GPU?
Oh,
I mean, okay. I mean, unless there was specific hardware that was created for deep learning models, that's best.
Maybe.
I don't know.
I don't know. Yeah,
Is there any sort of research into creating the specific hardware? Because I see that crypto had sort of revolution after some point when people were trying to increase performance. So does anyone know what?
I know that Google specifically makes something called a TPU, which is a tensor processing unit, which is very, very good at doing matrix multiplications. And actually, the chip that Sam, our guest speaker, had on that Movidius, those are using something called VPU, which are vector processing units. They just called it a VPU because their name GPU is already taken. Yeah, there's a lot of research into this type of hardware. Is there any questions on convolutional neural networks? Does anyone want more information on this? Does anyone know what a convolutional neural network is?
I'm not really sure.
Is someone?
So I have a question that's just a bit concerned understanding about I guess layers. So the class and the way the professor he just said that hidden layers were just a black box. You don't know what goes in, what goes out. It just happens, right? But then he also said you have to define the hidden layers, and I thought those two concepts were kind of counterintuitive. So how can you define something which you don't know what goes in?
So in any neural network, the hidden layer is in fact a type of black box oftentimes when people try to explain how a neural network works, they'll explain that like earlier layers will learn more concrete features like edges, and they'll become shapes, they'll become like a face, right? But this type of explanation is actually just like an explanation for humans to understand. We don't actually understand totally what is going on in those hidden layers. There is research into showing what those features are that are being extracted, but it's quite abstract for humans at least.
Yes. So in this paper, it also uses 8 layers, eight layers of convolutional network, and the 5 of them are convolutional layers, just explained in the previous slide, and 3 next are fully connected layers, meaning that whatever the output from the previous layer is directed into the next layer.
So neurons is something called an activation function, which is explained basically is some formula which calculates the input, or the weighted sum of the input and the bias, and it decides whether the neuron is fired or not. So in this case, they use something called a ReLU, which is faster than what was previously used, which is sigma more than 10H. So you can see in the pictures that ReLU, like 0, and to the left of the x-axis, it's all 0, but it just sort of increases linearly because ReLU is basically take the max of 0 for your input. And the researcher found that using ReLU as an activation function, it converged on a reasonably good error rate, significantly faster than the other. So, and the reason people, or at least according to Andrew, that the reason that ReLU wasn't used as much before because it was sort of like so simple that people were thinking this can't possibly be like, so simple. Why would it work over something that's reasonably
No, yeah, right.
Can we use a ReLU into a classifier to classify a network, like which one like classification?
You mean it's like an activation function?
Yeah. So like,
It's still used today.
You mean, you're probably asking like for the final probability layer.
yeah.
Right? That's what you're asking. That's a good question. So in the last layer, they don't use ReLU. Actually, they use something else to convert it into a probability, something like a soft max function. So this is like basically converts everything between 0 and 1.
What's the difference between the softmax function and an activation function?
So the softmax is the type of activation. Activation just means that it's transforming the input in some way. It could be a non-way. Yeah.
So it's just a different function.
Yeah. Does anyone have a question like what do activation functions do? What are they used for?
Yeah.
Yeah. You do have a question, right? Yeah. I can draw this on the board. Has anyone not heard of an activation function before this slide? So you have a neural network, right? And a neural network is able to model very complex functions. So a neural network, you have neurons, right? You have weights. So then at each neuron, it's just the weighted sum of some weight I times some inputs x I, right? So this is just plus some bias. So does anyone recognize this type of form? Why? What is this? This is a straight line, right? It's a straight line. So if your neural network was just composed out of all of these, if you add all these up together, a straight line plus another straight line becomes another straight line. Right? So if you have data, which is like the curve, then if you only had straight lines, you could only model a straight line with the neural network. But then how are neural networks able to model something so powerful? Have you guys ever used like Excel, where I don't know if you know, but there's like a polynomial fit function. So if you have like all of these dots here, and then there's something called like a polynomial fit function in Excel, you like figure out what the correct like x cubed, ax cubed plus like bx squared is before. Cool. So then the way it's able to get all these bends is that it's using these basically polynomial things to curve it. So the way neural network does this is that it uses an activation function. You notice that all these functions, they're not straight lines. They're not totally straight lines. Right? So what this does is that it adds a little bend in the function that the neural network is able to produce. So then when you add all of these little bends together, it can somehow make any function you want. So even if it's a straight line, you could have a bunch of little bends like that. Right? And it'd be a pretty straight line. Does that make sense? Question?
So ReLU is like better than all three?
Yes. And that was very surprising because what does ReLU look like on the right side? It looks like a straight line, right? And on the left side, it's actually also a straight line. Right? So people didn't think that this could possibly create these fancy bends that are needed. But it turns out ReLU actually works very, very well. Works a lot better than sigmoid 10H, does a lot faster to compute.
It's not only for the convolution network.
Mm-hmm. It's for any type of neural network.
Okay.
ReLU is used in all types of neural networks.
Oh, okay. I'd actually argue that the ReLU works better just because of its simplicity and just the mere fact that it has the property of free nonlinear.
Great, yeah, great insight.
What's the exactly meaning of non-linearity?
Non-linearity just means anything that's not straight, not a straight line specifically.
If it's not, if it can be defined by y equals mx plus b4, then it's nonlinear.
So how does this magic L-shaped line make it so magical at mapping this data?
Do you mean like compared to other activation functions? Okay, yeah. Yeah. So yeah, again, ReLU is very innovative in this way, and I think this was one of the first papers that introduced ReLU for the convolutional net. So one of the first activation functions was sigmoid. That's why it's on top. And people chose sigmoid because, well, it's between 0 and 1, and it looks kind of nice. So people are like, oh, it looks kind of nice, let's try and use this. But there's actually an issue with sigmoid and 10H. So you guys remember how a neural network learns? It uses gradients, right? It calculates, it makes a prediction, say like, I don't know, y, and then there's a true y. I forget if it's like y hat, y bar, something like that. It's trying to make a true y. And then there's going to be some error, right? Some epsilon error. And then if you remember your calculus, you can figure out which of your variables are contributing most to the error with gradients. So what is a gradient? A gradient is basically like a slope. What's the gradient here, for example? Roughly like 1, right? What's the gradient here? 0. So if you look at sigmoid, like something like that. That's it. Kind of head and down. So something like this. Yeah. Between 1, 0. So what's the gradient here? Right. 1. Right. Everyone agree gradient here is roughly 1. What's the gradient over here?
Approaching 0.
Approaching 0, right? So if the gradient is 0, the way a neural network updates its weight, something like the weight is now equal to whatever the weight was previously times the gradient. I draw a gradient. I'm just going to draw this for gradient. So if the gradient is 0, then if w is equal to 0 plus like gradient plus weight. Yeah, gradient plus weight. So if this is 0, w is equal to 0 plus w, it's just w, right? And then it doesn't learn at all. So that was the issue with the sigmoid functions that became 0 and they couldn't learn anymore. That's called the vanishing gradient problem. Make sense? Question?
Well, it's using a linear function, wouldn't that generate a gradient of 1 as well?
Exactly. So it's a gradient of, it's a constant gradient, right? Gradient of 1. But if you have like W is equal to gradient plus W, and the gradient is 1, well, it can still update.
But if it's less than 0, then the value dies. So what do you do with that one? Or I guess that's more research to be done there.
Yeah.
So, like when it's less than 0, then the value that's output is 0, so the value is kind of.
Yeah, correct. Did you have a thought to answer?
No. What is that W, the first W?
This?
Yes.
Oh, this is like W, like gonna be after, and this is like W before. So what's gonna be after is the change we're gonna add to what we have before.
What is the gradient?
What is W? W is a weight. That's a weight. Yeah. And then what is a gradient?
Yeah.
What is a gradient?
I think, isn't it an activation function plus the weight?
Oh, this is for when we, yes, when we go through the neural network coming forward is a different function. But this function is for specifically updating our neural network in response to the error. So we've already gone through the whole neural network. We calculated an error. Now we're doing something called backpropagation. We backpropagate the gradients, and then at every single parameter, we have that gradient, and we update the weight to adapt to the error. Maybe in 2 weeks we'll have a better explanation on this from maybe. Oh, I didn't answer your question about
They were dying early.
Yeah, so this is actually also a common phenomenon. ReLUs will die. So what they introduced instead is something called a leaky ReLU. Where there's like a small gradient over here. So even if it comes out like that.
Does that work in practice, and are there any negative benefits to it?
It does work quite well in practice. I don't quite remember what the specific pros and cons are, but I know there's a lot of research into what's the best activation function. People do all sorts of things, like they make this little curve, or they make this like a switch function, and things like that.
Won't any curve function, like any function that has a curve in it, reach 0 at some point? Because like the Banshee gradient function is introduced in every sort of function that doesn't have sharp edges. Yeah, that's a good point. So yes, technically anything with a curve is going to have a gradient somewhere maybe 0. But there are more complex weight update rules. So before I just had a gradient plus W, right? And the gradient becomes 0. So they actually add some extra terms onto that update rule. And this is called momentum. So if you have the ball rolling down a hill, it'll basically record how fast it was going before and then add a little bit of like a jump. So if it does get stuck, it can get out of that.
What if the cost function has global minimum?
Sorry, the cost function has what?
Global,
A local minimum?
Yeah.
Oh, yeah. It's like, they're trying to like, you'll stuck over here, right? Yeah, this is a very common problem in training neural networks. So that's also where the concept of momentum comes in, is that if it does get stuck in a local minimum, like maybe you can try and roll out. But this is like, I'm not saying this is a solved problem. This is still very much an issue. How do you implement that momentum? How do you implement it? Yeah. I forgot the specific math, but again, with the way update rule.
Actually, we have it on the slide.
Oh, we do?
Yeah, they give the form.
Oh, you want to go through it? So they actually use momentum in this paper, AlexNet, as well. Oh, yeah, there it is. That is?
Yes, very scary.
Oh, yeah. So the V term on top is momentum. Or, not necessarily momentum. It's the gradient plus some momentum term. We can go more into the math in future. Any more questions? Should we move on?
Hopefully it'll make sense to the rest of the slides.
You move on.
So, like somebody mentioned before, I can't quite remember who, one of the big things is that not only was it trained on one GPU, it's trained on multiple GPUs. So basically half of the neurons are on one GPU, and they go to another layer on the same GPU, then it gets transferred to a different GPU, and they use cross GPU parallelization, where basically there's no overhead for reading and writing in memory between GPUs. Does everyone get that? Good. This is one of the more complicated ones, but basically this function, basically what the function is doing is it's normalizing all of the values of the layer to be within a certain range. So like, for example, like sigmoid and 10H, they all fit within this range, but ReLU is kind of unbound. It can grow like as big as the highest positive number you have, and that can sort of affect the rest of the layers. So something they do is they sort of normalize it before it gets fed into that activation. That's kind of like a gross oversimplification, but it's one of those reasonably complicated, and there's a paper or a blog post that Andrew links. You view it aside that will explain a little bit. So I apologize for the brief oversimplification.
Yeah. So the next is about max pooling and average pooling. So max pool, and you can think of image as a two-dimensional matrix, and for what max pooling does is that it simplifies from certain areas in that matrix into one of the value as. So basically, what the max pooling does is it takes this four value and get the max value from this four, and similar to the following submatrix. And the average pooling, as you mentioned in the name, basically just getting the average value from this matrix and into the smaller part. So essentially, shrink the size for the training data for a better performance.
Is everyone good?
Any question? Yes.
So max pooling, if we increase the filter size, it would be 3 by 3, and then we would miss out on a lot of data when we're trying to take it. But then if we alter stride and if we increase the how do you think that's
Can you say it a little louder, please?
When you're doing the pooling, and if it's 2 by 2 filter, I don't think we're missing out on a lot when you're going to the next layer. But if you increase the filter size, we would miss out on a lot. But what about the stride? I don't know how it's going to affect.
I think stride would impact it potentially more on the edges rather than like that's just my opinion. I don't know if there's any math behind it, but I just feel like on the edges the stride would lose more data. But since there's more chance of you getting data in the middle of the matrix, the stride wouldn't really affect it. It would be better to reduce it.
Yeah, I think one of the part we forgot to mention in the convolutional part is that we have the padding, which is basically sometimes reduce dimensionality from the image. So image we can have different features, some related to color, some related to gradient, some related to edges, and the padding essentially what it does is it's sometimes it's getting the edge of the image, sometimes getting the center of the image, but mostly it's getting the center of the image and pad the value from the features into smaller matrix. Yeah, that's a question.
So if we increase the stride, then there will be more dimension.
There'll be more what?
The dimensions will reduce.
Yes. So essentially, your training data is smaller. Say you're training a 4K image, or you're training a one megapixel image. Usually I think the one you did before was like 128. It shrinks the image from like 200 megabyte to like 128 to 128.
But this is just sort of like a hardware view of the convolutional neural network and what happens with the GPU. Unfortunately, super qualified to explain this, but you can sort of just see how it goes from like the max pooling, it gets smaller and smaller until it gets to fully connected layers, and just sort of goes straight through. And then something we probably should have mentioned last time is like one of the major problems with machine learning is overfitting. Does anyone know what overfitting is? Everyone know what overfitting is? Okay, so basically overfitting is when your model gets a little too good at identifying the particularities or features of your training set, and it's not very good at generalizing for stuff it hasn't seen before. So like, for example, if in this picture on the left, you can see that the line is drawn captures some of the orange data points, but the vast majority of it is the green X's, which means it's not very good at stuff it hasn't seen before. And on the opposite side of the spectrum, you have underfitting, where your model is, they say too simple in the definition, but I think it's kind of weird. But basically, it's not very good at generalizing at all, and it performs poorly on both the training set and your test set. And then in the middle is where you want to be, where it's kind of reasonably good at both training and test set, and error rates are very similar.
The underfitting is it where the training is like 50%?
No, usually you just have kind of like a reasonably high error, like it's not very good at test or training set.
Yeah, it's usually kind of presented as a focal points. Basically, you can say if you want your model to differentiate between muffin and chihuahua, and it's getting as bad as Euclid performance. So that's
what create.
Yeah, go ahead.
No, I want to know the reason why it's underfitting. I thought maybe it's the reason is because the training tests say are equal, like 50-50.
Not essentially. Sometimes underfitting can caused by poor label data.
It's not enough data.
Not enough data, poor label data, or
it can also be like you don't train your model enough. Like if you have a huge amount of data and you don't have enough space to fit everything in, so you train it in batches and you only do like 1 or 2 epochs for only sees a small section of the data, it's very likely that it's going to underfit regardless of what data it actually saw, because it didn't see everything.
I said it perfectly.
Yeah.
When will the overfitting happen?
Well, it's kind of tough. I would say generally it's when your training set, test set are very similar and there's not a lot of variation. It's kind of tough to say without actually doing it because it's pretty easy to measure once you trained your model, because then you can.
I think overfitting happens when your test loss is way higher than your trained loss.
That's correct.
Yeah, that's not how you map it.
Any other questions? So then something they do to combat overfitting is data augmentation, which they do like image translations and horizontal reflections. And one of the big advantages of doing data augmentation, you can sort of artificially boost the amount of data you have. So for example, if you have images and you do a bunch of reflections and translations, you can get like 2 to 3 times as much data. And it'll help reduce the likelihood of overfitting.
But AlexNet already has a lot of data.
Yeah, ImageNet does have a lot of data, but applying these kind of techniques to your own project, sometimes you don't have too much data based on the data you're collecting. So doing certain,
I just thought we would still talking about it.
Okay. Yeah, because.
So they did use data augmentation in AlexNet, which is training on ImageNet. think the point is that data augmentation helps regardless of how big your data set size is. Because even though the number of images is so large, like, well, it still doesn't have like the same image, like translated a little bit, like from a different angle, like flipped a little bit. There's still, just because real life is so, I guess there's so many, like, it's so continuous in real life. Like even with however much data you have, it doesn't model like continuity. So this data augmentation doesn't.
Oh, and also, like, I've just read the abstract, and they said for regularization, they use something called dropout.
Oh yeah, we'll get to that very soon.
Oh, did you have a question on dropout?
Yeah, I wanted to get to it.
Oh yeah, we'll
I was skeptical about data augmentation. Like when I first heard the concept, it seemed like a neural network would be able to identify it, and it was just going to overfit. It would actually cause more overfitting than not, just because you are training it on the same image, and it just kind of in different orientations. There's nothing markedly different about the image, rather than just like rotation of the image.
That's from your eye perspective.
Yes.
Yeah.
So I mean, intuitively, it doesn't make sense. So I mean,
kind of adding on to that, because what the machine is actually doing is very abstract, and it's not what we see. Like transformations like that should ideally overfit the data even more according to what we think it's going to process. So how does it battle?
That's a good question. I'll admit I don't know each of the answer.
Yeah. I also would like to add to that, like, we're also implementing like the overfitting and then like minimizing the data from the data sets. Like, if we augment the data, like with the, like change our orientation a little bit, since we're pulling the data, considering use the same data, depending on the different translation as well. Let's just get
they mentioned in the paper, like for each overfitting, like compounding method, what error percent increase they got. So like how much this specific method reduced their error rate by. And I think most of them that weren't dropout was like, I want to say around 2% of a decrease. So like it already, because the data set is so massive that overfitting is kind of rare, that it wasn't a super big problem. It just sort of helped keep the error rate down.
I would feel like a large data set would cause more overfitting. And yeah, it would be a large data set would be a model trained on a large data set would be more prone to overfitting rather than less.
Why do you think that?
Well, because it has the ability to make a more complex polynomial function.
To fit more data.
More data, so therefore it'd be harder to generalize.
So my understanding, at least, is that like look at like less data versus more data. And if we had less data, like this is a circle, this is a X. And what if this was our only data set? This is a larger data set. Oh, and then we might like make boundary like this. What if we had a larger data set? Like this, right? X, X, X. This is what you mean, right? If you go more overfit.
Or a little bit more complex.
A little more complex. Yeah. I guess complexity does not necessarily mean that it's overfitting. Overfitting is where it's complex, but in the wrong way.
I guess my point was simply that the complexity, increased complexity makes the model more prone to overfitting, not necessarily that it does cause it, but as just an art, like it has a higher likelihood of it being overfit rather than less.
I know that when a model is more complex and the model is more likely to overfit, I think if the data just has more images though, this just makes it a better representation of the distribution that the model is supposed to fit onto.
I think as long as you label it correct, they contribute to the model, not actually make it negative.
I mean, overfitting is good because if you theoretically had like a set of every single image in the world, then you want it to overfit because it can match everything. That's everything made. So that's overfitting. Like If it's big enough, a little overfitting probably isn't that bad. If the variation you have in that set is likely to represent what it's going to encounter when you actually pull it.
And normally you will still training because you mess up your training data set, testing data, right? So you accidentally dump some portion of your training data into testing data.
This is a really good discussion. Just because we're giving you some answers doesn't mean that the answers are necessarily 100% right. We definitely encourage you guys to look this up as well, do this, and then come back and then share with everyone else. Share what you think.
That's the meaning for the discussion.
So the paper answers some of these questions about overfitting specifically. So there's like multiple forms of it. So there's RGB, there's image translation, and rotation. So there's multiple forms. So I think that kind of sort of answers the question.
You want to talk more about that?
So I just read about it. So basically what it's saying is that initially it takes a sort of the thing that we were talking about earlier, where it takes the image translation and the horizontal reflection, and then it extracts random patches of that image and then augments that. And then it uses another form. I don't understand the rest of that, but it's making those like full images out of those patches and then considering as images themselves. So it could, without taking the patches, that it says that it might suffer from substantial overfitting, but I kind of don't understand how it's working, but that's like one of the forms it's doing. And then the second part it's doing is that it's altering the intensities of the RGB channels in the images. So it's probably like changing color, hue, and all the different kinds of color settings, I would say. And it's using some sort of formula, eigenvalues, to actually calculate how much, how to change that.
Does anyone have the class at 3, by the way? Okay. Since it's 2:56, I also have the class at 3 at midterm. Okay, at 3. So thank you guys a lot for coming.
Yeah.
We didn't cover everything, but hopefully we can continue discussion online on Slack. Thank you guys so much for coming. And next week, our meeting is going to be Thursday at 11 a.m. We'll post the room and information in the Slack, but we're going to be doing the neural network coding tutorial on PyTorch again for a beginner's perspective. I hope you guys can do that.
If you still have questions, feel free to put them on the Slack or ask one of us. We'll be happy to help. Sorry? Oh, he's on Slack.
Yeah, he's also on Slack.
You could just go to like you could just when you look now.